Okay guys, welcome to lecture 9 of the database world. We started last time talking about physical uh, plan optimization, and we're still here doing physical plan optimization. The point we stopped at, we discussed the options the database engine has for doing a join. If you remember, we started the discussion with nested loop joins, or basically iteration join, and that's a type of linear scanning or linear relation access. This is what we've done. Now, the technique we're actually going to look at today is called merge join, which is going to be the second technique we look at in terms of joining two relations. Now, what this technique actually does, um, it tries to be a little bit smarter working with the two columns involved in the join. The assumption here is that the two columns are sorted from smallest to largest. So what this should hint to you is that we are talking about a type of a sort-based technique. Remember we said we have linear access methods, sort-based access methods, hash-based access methods, and index-based access methods. And under each one of those, there are many variations to support the different SQL operations. So what we're looking at now is a technique that you would use as part of a sort-based approach to doing the join. So you have to sort the column you're joining on in the two tables you're joining. So here the tables are R1 and R2, and the column that is common between them is C, the C column. Now, here is how this works. If I have the entries sorted in the two columns, where it says R1 of I.C, as you see, the entries are sorted 10, 20, 20, 30, 40. And R2 J.C, so it's the C column in R2, the entries are sorted 5, 20, 20, 30, 30, 50, 52. The idea was merge join, and this is actually a kind of variation of merge sort, although it's not really sorting, but this is where it gets the name from. What we're going to do is we are going to have these pointers I and j that are initialized to 1 both, as you see at the way left, I values goes from 1 to 5, and j values at the way to the right column, rightmost column, it goes from 1 to 7. I goes from 1 to 5 because we have 5 rows in R1, and j goes from 1 to 7 because we have 7 rows in R2. What we're going to do is we are going to advance I and j down the two columns, R1.c and R2.c, but in a way that guarantees that we're going to include in the result set all the values we expect to see as the result of the join according to what you have learned from database 1, the expected result from the join. What I'm referring to specifically is that if you look at R1.c, I would be pairing the first 20 in R1.c, which is at row number 2, with the first 20 in R2.c, and I need to pair it with the second 20 in R2.c, and I think the arrows show that clearly. And if you look at row 3 or when I is equal to 3 in R1.c, the second 20, I also would like to pair it with the first and second 20 in R2.c. And then the 30 in R1.c, I would like to pair it with the first 30 in R2.c and the second 30 with R2.c. So we need to advance and treat I and j in a way to make sure that That's the output we get. In other words, we cannot just increment I and j down the columns, and when we find a match, we include it. So when I find the first 20, which is at row number 2 in R1.c, and I find the second, the 20 in R2.c, so I match the 20 with the 20. I'm going to put a red line here that shows you what I'm referring to, like this one, the one that's labeled with this symbol or this mark, and then I'm done. What I need to do is I want to make sure that I also pair it with the first 20 on R1.c, which is at row 2. I want to also pair it with the second 20 on R2.c. Okay? So this is what we're going to do. As long as I and j are not pointing to similar values, so I will be pointing to 10 at row 1 and j will be pointing to 5. These are not the same value. I will advance both. But once I see the same value on both sides, when I is equal to 2 and j is equal to 2, I will see the 20 and the 20. What I'm going to do is I will look for other 20s that I can match with in R2.c. So I will advance the j down. I will find the second 20. So I will match the first 20 in R1.c with the second 20 in R2.c. Now, and then I will advance again the j. When I hit the 30, which appears in row number 4 in R2, what I'm going to do is I will advance the I down. When I see it's a 20, I will reset my j up to the 20 at row number 2 in R2 to be able to match the second 20 in R1.c with the first and second 20 in R2.c. So the logic is I and j are looking at values that are different, advance both of them. I and j pointing to values that are the same, like 20 and 20, then advance the j. And keep advancing the j until you find a new value. So now the turn is on the I. You go and check the next value. If it's the same that what you have been looking at before, reset the j up so you can do the match properly. So we get the desired result set.
Okay, so let's start looking at the merge join algorithm. As you see up there in step 1, the first thing we do is we sort the two relations that we're going to join on the column that we are going to join according to, which is the C column. So as you see, this is a sort-based approach to doing the join. Without sorting, this cannot be done. What we're going to do is we're going to use two variables, I and j, as I mentioned before, to compare the different values in the C column in both relations. If you look at the third line, it says while I is less than the number of rows in R1 and j less than the number of rows in R2, which is TR1 and TR2. We're just making sure that we don't get in kind of an out of bounds exception if we're doing this in Java, because we went beyond the last row in R1 with the I pointer, or the last row in R2 with the J pointer. And then the first thing I do inside the loop is I check if the C values are matching. If R1 of I.C is equal to R2 J of J.C, and I am going to output the tuples. And it says tuples with an S because I'm going to get one tuple from R1 and one tuple from R2, as you know, in the join, and I will include that in my result set. So let's look at output tuples. Now inside the output tuples function, this is what I have been describing 2 slides ago. What's going to happen is, as you see, that's highlighted in red, this JJ pointer is an additional variable that gets initialized with the value of j, and then I start moving the j downward. The j is the one that moves through R2. So while jj is not beyond the last row in R2, and as long as R1 of I.c is equal to R2 of jj.c, I will output the pair, which basically here it's going to be like, if we're just printing it on the command line, it's going to be like system.out.println. Otherwise, output pair here will be, adding an entry in the result set. I'm going to take R1 of I and R2 of jj and put it in the result set. That's what the output pair will do here. And then I will increment the jj by 1. This is the scenario we were looking at earlier, where we had the 20. Let me just draw it here for you. So we had the 20 in R1, and we had also 2 20s in R2. So the incrementation will have us match both of these guys with R1 of I, which is the first 20. And then in the last step, I increment I1 by a 1 to move in the R1.c column downward one row. And as long as you see here, we go back to the first while loop. As long as this, what we're looking at, R1 of I.c is equal to R2 of j.c, which is going to be the case if you think of the cases of the 20s, because we had 2 20s on both sides. Then we're going to go and initialize jj again with the value of j. Notice we didn't change j here, we're changing jj. And then I go inside the inside while loop again to output, or to pair the next 20 in R1 with the 2 20s in R2. And that's how this is done. Now the last part that remains, you will see it in the lecture in the next slide, is what is highlighted in red here. What actually happens is, after I have matched the 2 20s with the 2 20s, I would like to advance my I and j beyond what I'm currently standing at, and that will be the case because the if statement will fail if R1 of I.c is equal to R2 of j.c will fail. So when I come to the if, now what I'm going to do is I'm going to be a little bit smart in how I advance the I and the j. It will depend on who is bigger on both sides. Remember, we're comparing R1.c with R2.c. So if R1 of I.c is greater than the column on the left is greater than the column on the right, the c values, then I will increment the j. Else, if the column of the left, which is the second if statement, if R1 of I.c less than R2 of j.c, if the column on the left is less than the right, then I will increment the I. Now, what is the rationale behind this? So let's try to throw some numbers. Let's say you're getting a 10 here. So this would be for this case. So let's say you're getting a 10 here, and this is a 5. So what you'd like to do is you would like to advance the j to reach to the 10. While if, let's look at the next case, if this is smaller, if you have a 5 here and a 10 here, you would like to advance the I. And that's what this is doing. Okay, so the last point that remains with this algorithm is that, as you see in the while loop at the top, the algorithm breaks or stops working, or the while loop stops working when one of the two checks we are making fails, which is that I did not go beyond the last row in R1 and j did not go beyond the last row in R2. So if one of them, if the two tables are not of equal size, one of them is, say, smaller than the other, let's say R2 is smaller than R1, then there's no more rows basically, so you cannot advance the j, and consequently there is no meaning of going and looking further into R1 to see what are the other values for inside the R1.c column, because you have nothing to match with in R2.c, because R2 is done. And that finishes this algorithm. So what we're going to discuss next is the performance of merge join in terms of the number of IOs. As I already mentioned, this is a sort-based technique. So if it's just by accident that the two tables you're joining, R1 and R2, are being joined on the column C, and this happens to be the clustering column, so you're quite lucky. So you don't really need to sort the two tables on C, because it's already sorted on C. Now, so you're not going to do sorting. And if it happens that the relations are contiguous, and we went into an extended discussion about that in the previous lecture, contiguous means that you read one whole page, using one IO only. So you spend one IO and you read a page, while non-contiguous means you spend one IO per row. So if the relations are contiguous and R1 is sorted by C and R2 is sorted by C, that's quite a nice scenario, because what we are basically saying is that the cost of the sort-based merge join is going to be just the cost of reading R1 plus the cost of reading R2. And if you remember from our last lecture, R1 had 10,000 rows, and we were storing 10 rows per page, so we had 1,000 pages. So we're going to pay 1,000 IOs to read the 1,000 pages. And R2 had 5,000 rows, and again we're storing 10 rows per page, so we're going to pay 500 IOs to read all of R2. And notice that the way merge join work, and that's why we are discussing it here. It's an interesting joining technique from a performance perspective, because what we're doing is if R1.c and R2.c are sorted, then using the INJ we move generally from top to bottom, which means we don't have to repeatedly load pages. Now there is some special cases where the data will be so bad that actually we might run into a scenario where the number of pages we have in memory is very limited, and when we are actually joining R1 and R2, we get lots and lots of duplicates. So we will go back and forth reading pages from R1 and R2 to put them in memory to continue on. Like imagine, for example, the scenario we were looking at, we had 220s in R1 and 220s in R2. Let's imagine there's the extreme scenario of 1 million 20s in R1 and another 1 million 20s in R2. So obviously you will have to go back and forth loading pages from disk, putting them in memory, and then you run out of space in memory, so you take away the pages from memory and override them with new pages from disk. But that's a very extreme case. In most cases, when you're actually linking two tables using a foreign primary key thing or a foreign key thing, then you don't run into such a scenario. So generally we think of a merge join cost as being just the cost of reading R1 one time and reading R2 one time, which means one pass on R1 and one pass on R2, and that gives us the nice 1,500 IOs. And remember, like when we talked about iteration join, we went from 55 million to 60,000 to 55,000. when we stored the smaller of the two, which is R2, in memory, we divided it into chunks, and we kind of cached the chunk in memory, and we worked on R1. If you check the slides from previous lecture, we actually managed to bring down the 55 million to 55,000. But now we're seeing even better performance with just 1,500. But that's again, the assumption here is the relations are sorted on C already, and the relations are contiguous. Now, if you remember also, if I just to put things in perspective here, when we were doing our iteration join and we talked about relations were contiguous, we dropped even the number beyond 55,000, but I don't remember it now. I think it was 5,500 if I remember correctly. You should check it in the previous lecture slides. But even what we're doing now, we're even doing much better even than that. We're at 1,500. Now, what if they're not ordered, but the relations are contiguous on disk? So this is the more common scenario. If you're doing a join, then you might be joining on two columns that are not the columns used to cluster the data. So what the database engine would do, it would actually sort, or basically make a copy of the data, but we really don't think of this copying process. We just say the database engine will sort first before doing the merge join. Okay, now I kind of already explained this at one point. How can we sort things on disk? That it is actually two phases. It's not one phase. It's not like the sorting algorithms you've studied in CS3, because over there the data was in memory, while here the data will be on disk, and we have limited memory, so we cannot load all the data from disk to memory, which means we cannot just run a sorting algorithm from the beginning of from the first element in the data to the last element in the data in one shot. So we're going to divide it into two phases. Now, in the first phase, we are going to read individual pages and from disk to memory, and then we sort the page in memory locally. So local sorting means within the page, and then we put it back on disk. Okay. Now, the idea is I'm loading page by page, sorting it. So a page could come to me like having the values 100, 7, 1. So I have to change it, the order of the rows, it becomes 1, 700, and then I put it on disk. Now the next one might come to me, 40, 30, 50. So I have to do it correct. I have to change the order of the rows, it becomes 30, 40, 50, and then put it back on disk. So this is the first step. Okay. Now, using chunking here will not really help us that much. I have to read every page. So the notion of, okay, can I chunk the data and make, and is this advantage in any way? Is there an advantage there anyway? And the answer is no. You'll have to read page by page and put it back on disk. Okay. But in the textbook, it's described as you're reading it in chunks, but you're still paying, 1 IO per page anyway, because there's no benefit from actually keeping the page after you sort it in memory. You'll have to put it on disk to empty a space for the next page to put it in memory. So this is the first phase of what's called an external merge sort algorithm. Okay, so merge sort you will see in actually CSAN 703. You'll see it later on in design and analysis of algorithms, and it has it works, let's put it in its own way. And what I'm describing to you here is more or less what merge sort does, but merge sort works in memory. What we are doing here, a variation of merge sort that works on disk. Okay, so again, what I do as a first step, I go to every page, load it into memory, sort it, and put it back on disk. Now, what I'm going to do next is something very interesting. I will actually load again the pages that are locally sorted, but I will load pages that have overlap in their ranges. So for example, and that means I have to keep track somehow of what is the minimum and maximum value in every page. So let's say one page starts at 1, the minimum value is 1 and the maximum value is 10. And another page, the minimum value is 50 and the maximum value is 70. Do they overlap? So again, 1 and 10, 50 and 70. They don't overlap. So I'm not really interested in them. I'm interested in pages that have an overlapping range. So for example, one page starts at 1, minimum is 1, maximum is 10, and another page starts at 5 and the maximum is 12. So these guys are overlapping. So I will load pages that are overlapping, sort them correctly in memory by moving rows between those two pages, and put it back on disk. Okay, now I'm describing to you here in kind of a high level detail, or the high level, in a high level way, without lots of, without the specific details. But you can imagine scenarios that you will have not just 2 but maybe n number of pages that have an overlap, like one page that will go from 1 to 10, minimum to maximum. Minimum is 1, maximum is 10, and the second one is minimum 5, maximum is 15. The third one is minimum 4, maximum is 20. So you figure, okay, I need to merge these guys together. So you would load them, and if the memory is not helping you, you don't have enough memory, you would load 2 at a time, or 3 at a time, or half n at a time. Fix the rows, which means move the rows between the pages so you have, there's no overlap between the entries, and then you start putting back the pages on disk and load the next set, and this continues on. Okay, so again, there is one pass where we read, we do local sorting, put it on disk, and then we read again from disk and do merging between pages, and then put it back on disk, and now you have the data. Now you have the data set. Okay, so in terms of cost, in terms of the cost for doing this activity, an external merge sort approach, what we're doing to each tuple is that I'm reading it, I'm writing it. The first read and write is you could think of this as per the tuple, but it's also per page, because I'm spending 1 IO per page. I read it, I locally sort it, and then write it to disk, and then I read it again to do the merge and write it back on disk. So 1 IO to read, 1 IO to write, 1 IO to read, 1 IO to write again. So that's 4. And if I'm spending an IO per page, and I'm going to do that 4 times, so I will spend 4,000 IOs to externally merge sort R1, and 2,000 IOs to externally merge sort R2. Okay, so now the cost, we'll have to add this to the cost of the next phase that we've already done, which is doing the join, which was standing at 1,500. Okay, so the total cost is, the sort cost is 6,000 IOs and 1,500, as I mentioned, for the join. So in total is 7,500 IOs. So now we are doing actually worse than the last version we've seen of iteration join. Okay, so this is something that I think should be surprising to you. And this is why I mentioned at one point that sometimes convincing the database engine not to do sexscan is difficult, because the database engine would be doing these computations and figure out, okay, I'm not going to do sort based merge join because it's more expensive, it's taking more IOs than a simple iteration join technique. So this is our finding up till now. Okay, so the general rule, just before we move on, if you're asked what is the cost of doing merge join, sort based merge join, where the column you're joining on is not sorted, you can simply compute it like this. It's 5 times multiplied by the number of IOs to read the pages of the 2 relations. So one of them had 1,000, the other one had 500, so it's 1,500. You multiply it by 5. 4 of them to do the sorting and 1 to do the join. Okay, so it's 5 multiplied by 1,500. Now, as I already mentioned, this is worse than the last version of iteration join, which was 5,500 IOs. Okay, No, but this is just a computation for our specific example that we are looking at. So if I play with the numbers, and here is just a proof to that, again, the relations are contiguous, but the values are not ordered, but I have a different number of blocks. Okay, if you do go back and do the same computation we did before, okay, using the same number of memory slots that we had, which is 101 slots, iteration join will give you 500,005 IOs, while merge join will give you 75,000 IOs. So merge join actually will be better. So what this is telling you is it's not always the case that iteration join will win. It depends on really a number of factors. The first one is what is the size, the number of pages in the relations you're joining, whether the relations are contiguous or not, whether they are ordered or not, and what's the amount of memory that's available for you to use. Here up till now I'm using, and I'll continue doing that because this is simpler to demonstrate. I am using 101 memory slots, and I'm doing something that's a bit naive. I'm allocating 100 to one relation and 1 to the other. Obviously there are other combinations that will produce different numbers, and that's a topic by itself that you will learn how you can do it by using a technique called dynamic programming in CCAN 703. I mean, it's really another example of what we call an optimization problem, where you would like to find the right division between the two relations. I mean, the memory division. If you have 101 memory pages available for you to use to run this specific SQL that is doing the join, should you split it 101 or 55 and the rest, or 50 and 51? That number by itself is, you're going to do an exercise actually to figure out what is the correct division. But here in my lecture slides, I'm just working with 101, and based on this scheme of allocating the memory, as you see, merge join now will wins if I change the number of pages. Okay. Now let's move on. So we've seen iteration join as an option. We've seen sort-based merge join as an option. What options do we have, or what options that the database engine decides to evaluate when it's building the physical plan? It's going to be, is it a good idea to actually use an index to do the join? Even if the index does not exist, it might decide to build the index, to do the join. But let's here assume that R2.C already is indexed for one reason or another. So remember, the join is really nothing but a sequence of searches to find, given a value from one relation, if it exists in the other relation. So if R2.C is indexed, we are going to actually search in R2.C for values that we get from R1.C. So the pseudocode looks like this. It says for each R that belongs to R1, do the following. So you're going to go to R1, read it page by page, and in every page you're going to read row by row, and you're going to look into R2.C index. Okay. Now, and for all the matches that you find in the index, okay. Remember again the example we had was 220s in R1 and 220s in R2. So let's say you search for 20 in R2 index and you get back the result that actually there are 220s. This is what the inner loop says. It says for each S that belongs to X. So this X will be the set of 220s. Okay, I will output R comma S, which is 20 comma 20 pair, which is basically a tuple from R1 and a tuple from R2, where the C is 20. Okay, so here I'm using the index basically to do the join. Okay, now for the purpose of the coming few slides, I will reverse. I would say that we will assume that R1.C is the one that has the index, and R2 is contiguous. So I will spend 1 IO to read a page, but it's not ordered. Okay. more realistic scenario here, given our running example. That's why kind of this is reversed from the previous slide. If R1 is the primary and R2 is the foreign, most likely the foreign is not, the R2 is not sorted according to the foreign key value. I will make the very important assumption here that R1.C index fits in memory. Okay, so we're not going to actually pay IOs for working with the index for now. Okay, so again, the assumption here is R1.C index exists, R2 is contiguous, and it's not ordered. So let's do some computations. Remember, R2 had 5,000 rows, 10 rows per page. So when we are saying it's contiguous, so I will spend 500 IOs reading all of R2. Now, for each tuple I get from R2, from a specific page in R2, I will go and look up in R1.C index. That's free because the index is in memory, so there's 0 IO cost. Now, if I find a match, I need to get the tuple itself. Remember, the index just have the value and a pointer to where the tuple is. So the tuple could be anywhere. So I'm going to, it's in some page on disk, so I'm going to spend an IO to read that page that has the tuple, to be able to read the tuple to put it in the result set. So this will repeat with every time I'm querying R1.C index, because at one point I might be asking, okay, R1.C if 20 exists. So it's telling me, yeah, 20 exists, and it exists in this page on disk. So I go and load the page. The next time I ask, you know, because I'm reading the 20 from R2, the next row in R2 might be the value 700. So I go into R1.C with 700 and I say, okay, in the index, the 700 exists. So it tells me yes, and here it is. It's on another page, completely different page than the one that had the 20. So I go and read that page to get the tuple for 700 to include it in the result set. And this continues on. So every time I go to R1.C, I find a match. I am paying 1 IO to read the page that has the tuple. Okay. So here is one very important question to understand the cost, the IO cost of this. You know, what's the expected number of matches every time I go to R1.C and ask, does this exist? Okay, so we have a number of cases. In the first case, more common one is R1.C is key, it's the primary key, and R2.C is a foreign key. So if I'm going to R1.C index and asking for, you know, does this exist? I will be told yes, and I will be told there's only one of it because it's a primary key. There's only one of it. It's unique. So I will expect always to get back an answer that has one match. Okay? So that means the total cost is the following. 500 plus 5,000 multiplied by what? Multiplied by 1 plus 0. Okay, what is that? How is that being computed? The first 500 is for reading all of R2, because again, R1.C index is in memory. I'm not paying anything for that. R2, the relation, R2 as a relation, it's contiguous, but it is on disk. So to read the 5,000 rows, and I have 10 rows per page, I will spend 500 IOs to read all of R2. Now, when I read all of R2, how many rows I have? I have 5,000. So I am going to go to R1.C index 5,000 times to ask it, does this value exist? And I will get an answer saying yes, there is one match, there is one key that corresponds to this. So if I say, do you have a 20? I got the 20 from R2. And if I go to R1.C index, I say, okay, do you have a 20? It will tell me, yes, I have a 20. And here is the reference to the page that has this 20 in R1. So how many times I'm going to go to the index for R1.C to ask? I'm going to go 5,000 times because I have 5,000 rows in R2. The asking the index has no cost. But when I find a match in the index, there is an associated cost with every match, which is reading the page that has the row. Okay? Now, how many times I'm going to go to the index? 5,000 times, which means I'm going to go and load 5,000 times a page, or I will spend 5,000 IOs because R2 has 5,000 rows. So I will repeatedly ask the R1.C index 5,000 times, and with every time I will find a match, and with every match I will go and read the page that has this row from this, and that's why we have a 5,000 here. Multiply by 1 because basically I will always find one match, and I will always read one page. Okay? And the 0 at the end is because the index is not costing me anything. So the total here, if R1.C index fits in memory, is 5,500 IOs. Okay? That's the first case. Now there is another case. R2.C references R1.C, and R1.C contains duplicates. So R1.C is not a kind of primary, not necessarily a unique. Okay, it's not a unique column. It has duplicates. So when I ask R1.C index for 20, it's not guaranteed that it will tell me it's 1. There's only one 20. It might tell me there are 2 20s or 3 20s or 4 20s because there are duplicates. Now, how the database engine estimate here the number of IOs? It will use the stats that we are maintaining for the logical plan optimization purposes, for cost-based optimization, to figure out on average how many matches will exist every time we go to the index and ask it for a value. So if we are told that the number of unique values in R1.C is 5,000, and we know that R1 has 10,000 tuples, has 10,000 rows, but we have 5,000 unique values. With the uniform distribution assumption, I expect that every time I go to the index and ask, okay, get me a match, I'm going to get back 2 matches. Okay? And then I will go and have to read the 2 pages that has these 2 matches to include them in the result set. And that's what you see down there in the last line. It says that the total cost is 500 for IOs for reading all of R2, plus going to the table, going to the index, R1.C index 5,000 times, and every time getting 2 matches on average, and then multiplying 5,000 by 2 get you the 10,000, and the index is still, we are happy the index is still in memory, so we're not paying anything for the index. So the total now is 10,500 IOs if R1.C has duplicates. And obviously here there is a lot of assumptions that might not necessarily be accurate. The most important assumption here I'm talking about is that I'm assuming uniform distribution. So if you would like to enhance that, we've already discussed histograms in the lecture about logical plan optimization. So you could enhance this number or make it a little bit accurate with histograms instead of just a number of unique values. Or you can even make it even more accurate with histograms and unique values per histogram. So you get a better estimate of the number of IOs that will be spent. And also there's another assumption here, is that when I get 2 tuples on average, that they will fall in 2 different pages. And we make this assumption because it's the worst case. But obviously there will be cases where you will save some IO because you end up with 2 tuples that exist on the same page. So you pay 1 IO, not 2 IOs. So I'm multiplying always the 5,000 by 2 as a worst case. Now, what's the third case? Well, R2.c references R1.c. We're working with the same example. R1.c contains duplicates. It's the same example we mentioned before, but we don't have any stats. So if we don't have stats and we work with the domain and you haven't defined the domain properly, the database assumes the domain based on the data type, you can go off with really bad estimations here. Okay, so that's why it's important that when you work with a database engine, you understand what kind of stats it uses, and if it is not keeping track of the number of unique values or histograms and it's just using the domain, you got to be suspicious about the database engine, and you should think carefully about using it or not, because if the domain is built from the data type, then if you say that you have a column that is a varchar of 6, what the database engine is making or is assuming is that all possible combinations of 6 letters is the domain. So there will be an explosive number associated with the number of possible values for every column. Like, for example, here, if I assume that the domain for the C column is 1 million, so you see that the number of IO now is ridiculously small, okay? Just because I've enlarged the domain a lot, okay? So this is our summary. In case 1, we had the situation of a primary foreign key. We got this much. In case 2, we had duplicates in a foreign key. It's this much. In case 3, we actually worked with a domain that was not carefully computed, so you suddenly see an unrealistic drop in the number of IOs. Now we come to the issue of the index. You see, when a SQL statement runs in a database engine, it's always running in a constrained memory space. I've talked about this before, that SQL statements are not allowed to abuse the resources when they're being executed. So in most of the cases, a SQL statement is running with a limited memory within the database engine. So what I have assumed early on, which is that R1.c index fits in memory, well, let's think of it as a B+3. We already learned that with B+3s, only the root is kept in memory and the rest is on disk. Okay, we are not allowed to abuse the memory by just loading the whole B+3. Imagine that the table has 10 million rows. So are you going to go and load a B+3 for 10 million values? Just that every once in a while you use it? Well, obviously not. You're going to keep the root, and when you'd like to actually query a value, you go and load the pages that, or the nodes that has along the path that is interesting to you. So if you go from the root to a specific leaf, then you just load the nodes along this path. Okay, so let's actually work an example to see the effect of this on the IO computations. Now I will assume here that the index is 201 blocks or pages or nodes, where I'm storing every node in a page. Okay, I will always keep the root plus 99 leaves or leaf nodes in memory, and the rest is on disk. Okay, it's just a setup for you to get a sense of the cost that's involved here. That is not necessarily exactly how things will run. Most likely we're keeping just the root and a smaller percentage of the B+3 in memory if we're doing some kind of caching of nodes in memory, because we notice that a specific path is being traversed repeatedly. So, but again, I don't really talk about this within the scope of this course. The assumption always is that we keep the root in memory and the rest is on disk. But let's say we keep half the B+3 in memory and the rest is on disk. Okay? Now, the question is, with every SQL statement execution, what is the cost of working with the B+3? Well, if the part of the B+3 that you're working with exists in memory, there is no cost. There is 0 IO.
If the part of the B+3 you're working with exists on disk, you have to load it. So this turns out to be a probability problem. What's the chance of going to disk? We can ask about it this way. Okay, so if I say that 99 out of the 99 out of the 200 it's in memory, 99 out of the 200 in memory, then it's 0 IO. And that's what you see down there in the last line. The cost is 0 IO multiplied by 99 over 200. Okay? Now, if you're going for one of the others that are not in memory, the 101 that are not in memory, what's the chance of actually hitting one of them? It's 101 divided by 200, because we will always keep the root in memory. So as I say, we have 201 nodes in this B+3. The root is always in memory. So now we're talking about the rest. The rest is 200. So 101 out of the rest is on disk and 99 is in memory. So the chance of paying an IO is 1, which is the cost of an IO, plus 101 divided by 200. Okay, that's the chance of or the expected value of the number of IOs we pay using this probability distribution and way of thinking, basically. Okay, because I don't know where I'm going to go next in the B+3. So the chance is almost half. Half the time I will go to disk to load a page, and half the time I won't. Okay, but there's no point of, there's no meaning to say half an IO. It's either 1 IO or 0 IO. But probability wise, we can talk about it as the expected value if we keep running this till infinity. Okay, on average we're paying half an IO. So I'm going to take this half and incorporate it in my formula. So before we said for case 1, which we worked with primary foreign key situation, it was 500 for reading R2 plus 5,000 for going to the index, and with every probe in the index we went and read a page. That's why we have the 1 in the second line there. Plus I'm going to add to that I have half an IO on average to load the B+3 nodes that are on disk and put them in memory to be able to work with them. So it's going to be 5,000 multiplied by 1.5. And that gives us 8,000 IO. So we have increased a little bit the number of IOs, which is more realistic, because usually, actually, this is even, I wouldn't say completely realistic, because usually B+3s are kept mostly on disk, so we'll be paying more IOs. But if you just, think of this example where with this specific distribution, then we are saying it's 8,000 IOs. Okay. Now for case 2, I'm just going to do to the same formula. Look at the same formula we've seen before. I'm just going to add a 0.5 to the 2 that we were having, was 2 on average. Okay, but every time since we have duplicates, every time we go to the B+3 and ask for a match, we get 2 rows. But now, while working with the B+3, again I have half an IO to pay, because half of it is on disk and half of it is on memory. So now this is my computation standing at 13,000 IOs. And the case 3, which was a trivial case because the domain was not really accurate, even that increases a lot. Okay. So we just finished joining with an index. This is what the database engine will do. It will actually compute the cost of iteration join, sort-based merge join, and index join to figure out which one is the optimal one, which one is the fastest, which one will use the smallest number of IOs. What it will also do is evaluate hash join as an option. Okay, we've already discussed working with hash joins before, but again, I will refresh your memory. The idea is very simple. If we use a hash-based scheme, or basically we're building a hash table, and we use a hash function that will make the inserts fall into certain buckets, and then we go and build another hash table with the same hash function. The same value will fall in the same bucket. Okay, so most of the SQL functionalities can be done later on by comparing or working with corresponding buckets. Like I have here an example. If I have the same hash function h that with producing a range from 0 to k, that's the output will go from 0 to k, and I build a hash table with buckets on R1, or hash table of buckets on R1, I will go creating buckets from G0 to GK, and I have R2, and I will get the column that I'm joining on, and I will build a hash table, so I will get buckets from H0 to HK. Any SQL functionality or operation I would like to do can be done usually by just comparing G0 to H0, G1 to H1, G2 to H2, and it goes like this until GK to HK. Okay. Now, and this is the algorithm I have just been describing. I will hash R1 tuples. When I talk about R1 tuples, I mean R1.c, the column that we're joining on. So this should be written as hash R1.c tuples into G buckets, hash R2.c tuples into, or R2.c into H buckets. Okay. And then match the tuples in J sub I and H sub I buckets. So here's a trivial example just to get you thinking about all this. If these are the two relations I'm trying to join, so this is R1.c and R2.c, and I'm joining on this column, and my hash function is trivial. It's going to be, if the value is even, put it in a bucket. If it's odd, put it in another bucket. So I can do that by taking the mod of an even number, 2, mod 2. Now, R1 buckets are shown on the left, and R2 buckets are shown on the right side of the slides. Now, if you look at R1, it says 2, 4, 3, 5, 8, 9. That's in the column on the left. And if you look at the R1 buckets, 2, 4, and 8 because they are even in one bucket, and 3, 5, 9 because they are odd in another bucket. Same thing for R2. All the even entries are 4, 12, 8, and 14. And all the odd entries from the R2 column 5, 3, 13, and 11 are in another bucket. Now what I'm going to do after building these two hash tables, there are two separate hash tables, one for R1 and one for R2, I'm going to match corresponding buckets. So I will match bucket 0 in R1, which has the 2, 4, and 8, with bucket 0 in R2, which has the 4, 12, 8, and 14. Okay, I will find that 4 is common and 8 is common, and that will be going to my result set for the join. And then I will match the buckets 3, 5, and 9, and 5, 3, 13, and 11, so I will find that 3 and 5 are common. Okay, this is how basically it works. Now, what about the cost? Now, if I assume that R1 and R2 are contiguous, which means I pay 1 IO for one page, and I'm using 100 buckets, okay, this is how this will work. I will read R1 separately and hash it and write the buckets. Okay, so that's 1 IO for reading all the pages in R1. The hashing is done in memory, and then writing the buckets to disk. So if we decide to think about the performance of this approach in terms of the number of IOs, what we're doing is we're reading all of R1, which is the 1000 pages. That's paying 1000 IOs, 1 IO per page, and then we will write the buckets to disk, because for the same argument, if R1 is too big to fit in memory, most likely the hash table is not going to fit in memory, so we're going to write it back to disk. And then we're going to do the same. So if the write that's in the first line means we've constructed the hash table and we've written the buckets to disk. We're going to do the same for R2. I'm going to read all of R2, so that's paying 500 IOs, plus writing the buckets to disk. So that's another IO. So now after the second line, what we have done is we've read all of R1 and R2, we've created the hash tables, and we've put them back on disk, the hash table buckets. Now, we didn't do the matching yet. So what we're going to do is we're going to load those buckets and match each corresponding buckets. Okay? And when we find a match, let's say 20 here and 20 there, 20 in R1 bucket and 20 in R2 bucket, what we're going to do is we need to go and read the page that has the 20 in R1 and the page that has again the row in R2. So I'm going back to the table that's on disk for R1 and R2 to get the actual rows that I will include in my result set. So that's an additional I/O. So reading all of R1 is one I/O. One type of I/O. Then writing all the buckets is another I/O. Also involves an I/O. Then reading R1 again to get the actual row is another I/O. So we have 3 of them. So generally, it's 3 multiplied by the sizes of the sum of the sizes of the 2 relations. So the 3 is reading R1, writing the buckets, and reading R1 again to get the row. So the first read of R1 was to get the key that I'm inserting into the hash table. The second read of R1 is to get the actual row that has this key to include in the result set. So in some textbooks, if you are actually consulting other textbooks than the course textbook, you will find that they actually add the cost of reading the bucket from disk to do the match. So again, let me revise this. If you look at the first line after the title, it says bucketize, read R1 plus write. What are we referring to here? Reading all of R1 to be able to build the hash table. And then writing here means writing the hash table to disk. And then reading all of R2 to bucketize or to build the hash table. And then writing these buckets back to disk. Now, we didn't finish. We just built the hash tables and we put them on disk. There's an activity in the join process. You know, the first activity we do in the join process is we're going to read corresponding buckets. So some textbooks will consider that also as an I/O, and some don't, because usually there is a lot of caching happening in here. So you can get away actually without computing it. But I will not go into detail of this part here because it's not mentioned in your textbook. Okay. Now, in previous offerings actually of the course, I used to teach it in detail. That's why when you will look at sample exams and quizzes, you will notice that sometimes we are actually computing the hash join by multiplying it by 4, not by 3, to incorporate the additional reading for the buckets. But for this offering, and what I have been doing for at least the last 2 years, is we're multiplying by 3, which means we're computing read, write, and read. So this is where we are currently standing. This is what the database engine is going to do. It will evaluate or estimate the number of IOs for every one of the techniques we have been describing. And as you see here, the one that is currently winning is the merge join, standing at 1,500 IOs. So this is the one. If we were running inside the database engine and that was our stats, then that actually the one is going to be picked, the merge join. Okay, and obviously these numbers changes as you change everything that you're working with. If you change the number of pages, if you change the number of duplicates, if you change how many memory slots you have, if you change how you distribute the memory slots, and all this is being computed per SQL statement that arrives into the database engine. Okay, so that means that you could run in one instance a specific SQL statement. And actually, there's a way in all advanced database engines to tell you the plan of execution. You will see that in your mini project 2, inshallah. So you will see the plan, how it's actually going to execute it, what kind of relation access methodology it's going to use. Is it going to use merge join or iteration join and so on? So you might run a specific SQL statement, and then you print the plan and you see, okay, it's using merge join, and then change the data and you run the same SQL statement and you see suddenly it's actually changing that and telling you it's going to use hash join. Okay, so this changes from one run of the same SQL statement to another. Okay, so the takeaway of all this is that the query optimizer picks the most efficient method to execute a specific SQL operation for inclusion into the physical plan. It does this by calculating the number of IOs to be performed. The IO will differ based on the given query and the existing data in the queried relation. SQL join can be performed using one of 5 methods: nested loop, iteration join, block nested loop, iteration join with chunking, sort merge join, index join, and hash join. Okay, so here I'm actually differentiating between the 2 types of iteration join, whether you're using chunking or you're not using chunking. Because in your textbook, this is how actually it's spelled out. So if we talk about just nested loop, that means there's no chunking. If I talk about block nested loop, that means I have chunking involved with me in the iteration. Now let's come to the final topic in this part of the course, talking about plans, is the notion of how can we construct all these variations. What we have been describing is, I hope it's interesting to you, but there is a problem. This sounds like a little bit crazy, because if you're trying to build, let's say you get too excited after you've done mini project 1 and you would like to build your own database engine. Okay, how can you generate different relational algebra trees from the parse tree? Or how can you generate different physical plans? Well, if you just think about the relational algebra tree one, well, you've learned in database 1 about the what's called equivalence rules in relational algebra, and as I mentioned, I will put a handout about this on the MAT website. But still, the space is really, really huge. Okay, if you just think about binary, which means you're not gonna translate a parse tree into a general tree, but you're going to translate a parse tree into just binary trees, where at most you have 2 children per node. You're talking about a huge variation, as I've tried to highlight, and at the bottom here in this slide, you see like this is the same query. You know, I have 4 relations, A, B, C, and D, and I'm doing a join. I'm joining it. If you 4 at the left, I'm joining A with B, and then the result was joined with C, and then the result joined with D. Or I could do it in another way by having A and B and then join with C, join with D. That's from a theoretical point of view, that's a different binary tree. Okay, so while you are able to generate the first one to the left, you should also think that the second one and the one in the middle is actually a different one. It will give you, the same sequence of operations because you're joining the same relations, but it's a different tree. And you have to count it, or you have to at least realize it's a different tree in terms of layout, but it's the same operations. But if you look at the third one to the right, or like the one that's to the right most of the slide, it's a completely different way of working, where I'm joining A and B and then joining C and D and then joining all of them together. Okay, that's just for binary trees. So if you imagine general trees, which is not binary, any size, then we have even a bigger number of possibilities. Okay, so if you just look at binary trees, how many binary trees can we have? Well, this will take us to combinatorics. Okay, the number of binary plans we have, if n is equal to 4. Okay, if we just have 4 nodes, we have 336 possible trees. If you don't believe me, plug in the number in the formula at the bottom. You should get this from your calculus book, combinatorics and permutations chapter, and you should see this because this is how many ways we can combine the 4 nodes. What if we have 5? Okay, we have 1008 possible trees. Okay, so this sounds like very explosive, and it is, because there is a factorial there. Even though you're doing division, but there is a factorial there. So whenever you see a factorial, you should, like, your hair should stand. We don't like factorials. Okay, so what do database engines do? Well, obviously they don't look at all possibilities. Imagine you have a SQL query that has nesting or several nesting inside it. So the tree that's going to come out, like say you're doing a really bad SQL query with, in which you join 7 tables together, and you have these 5 or 6 conditions and 3 or 4 nestings. So the tree is going to be really big. Okay? So this is how we think of things in the database world. Okay? Now we're only interested obviously in relational algebra trees. While when I was describing in the previous slide binary trees, I didn't talk about relational algebra ones. I'm talking about all kinds of binary trees. Okay? Now, relational algebra trees are a subset of all binary trees, even, or let me put it this way, relational algebra binary trees are a subset of all binary trees. Okay? Now, and relational algebra trees themselves, could be not made binary. In fact, if you look at the 3 or 4 lectures ago when I showed you a parse tree, I could translate that directly to a relational algebra tree. So we are talking about relational algebra trees that are binary, and we will call that enumerable plans, or these are plans that actually we can think of enumerating. So I'm not going to try to translate or keep a parse tree as is and work with it as is, but actually I will try to always work with relational algebra trees that are binary. Okay? And for me, those will be the ones of relative interest, I would say. Those are the ones that we can think of and manipulate and figure out what can we do with this, type of tree. Okay? But that's what we can enumerate. That's not what actually we can generate. What we actually can generate is what's called surged plans. Okay? So what we do in the database world, we are interested in performance, and because of that, we don't like the notion of loading many relations or even opening pages from many relations at the same time. So what actually we do is we try to gradually open relations that we need to answer a query. I mean by open means to start loading the first page of that relation. So what we do is we focus on binary trees that are called left deep, which means they are kind of skewed to the left. Now, it will turn out that this skewness is actually an advantage for us, because this means we can feed relations into the physical plan slowly or gradually, one level, as we go one level up in the tree. Okay? Now, the ones actually that we construct are called the constructed plans, or the ones actually that we run. Okay, so to give you a summary of what I'm trying to say here is that we're not going to try to evaluate all possibilities to figure out what is the most efficient tree to work with. We will restrict ourselves to a certain variation of binary trees that are called left deep, and these are the ones that actually we try to evaluate, okay, or find alternatives between. Everything else we will just ignore, because we can't afford to generate n factorial something trees and figure out, even by just estimating things, it's just going to take a lot of time, a lot of computational time to actually generate 1108 or even a small subset of that trees, and then figure out, okay, what's the number of IOs and what's the number of what's the size, estimated size of the result set that gets propagated, which is what we did in cost-based estimation. We're not going to do that to 50 or 60 trees. We can't afford to do that if we're getting a flood of SQL statements sent to the database engine in a single second, and then for every SQL statement we're going to generate or do an estimation for 50 different trees. It doesn't work like this. There's no time to actually do all of this. Okay? So this is what I try to highlight with this, that we're not interested in all plans. We're only interested in relational algebra plans. We're not interested in all algebra plans, all relational algebra plans, because if you think of all relational algebra plans, you're talking about non-binary trees. We're actually thinking only about binary trees, and not all binary trees, actually. As you will see, we're thinking about or evaluating skewed or left deep binary trees. Okay. So what's this story of left deep binary trees? A left deep binary tree is a tree in which the right child of each join is a leaf. Okay, so it's skewed to the side. Why are we doing it this way? Because since this is a leaf, this is going to be a relation. Because, you know, at the end, these trees are fed the relations from the bottom. So if it's skewed to the left and it's always having a leaf to the right, then I can always feed a leaf through the right child. And since this is binary, I can have at most 2 children per node, and the right child is always going to be a relation, then I can gradually feed in the relations as I go up in this tree. So I don't have to open and load many pages from many relations in one shot. When I'm done with one level, then I can get away or erase from the memory the relation that existed or was used at the lower level. Okay, so I can always load one relation, work with it at one level in the tree. When I'm done, remove it from memory, go up in the tree, load another relation, work with it, and then remove it from memory and replace it with another relation, and so on. Okay? And this is what this is all saying. It says, as results are generated, these are forwarded to the operator higher in the tree hierarchy. Intermediate results not written to temporary files. Okay? Now, the story is not as simple as it sounds, because if you look at the last point, it says not all left deep trees are fully pipelined. Okay, what we're describing here is often referred to as pipelining. You should have heard about this in the microprocessors or computer architecture course, as well as in operating system. This notion of creating a pipeline where we feed things in a gradual way instead of just, you know, loading everything in one shot. Okay. So here's an example of the pipeline I am referring to. Okay, as you see, this is a left deep plan. You look at the right child, you're always feeding a relation. If you look at it from the bottom, the one at the left, I'm joining R1 and R2. The result of this join is going to be joined with R3. The result of this join is going to be joined with R4. This is what we describe as pipelining. You know, I'm introducing one relation at a time as I go up in the tree. Okay. Now, these are 2 different, as you see, left deep plans for the same query. At the end, I'm joining R1, R2, and R3 and R4 together. But the order of the join here makes them two different trees. Okay. This is actually what gets evaluated as options, as alternatives, when we are generating physical plans. Okay, which one should be picked based on the I/O estimation. And obviously, again, we're not evaluating all options. We're just working with this subset of representation. Okay. Now, even with left deep plans, it's still a lot of work. Okay, so left deep binary plans are a subset of binary plans, which are a subset of all possible plans. Okay, but it actually helps us a lot because it decreases the number of possible trees that the database engine needs to evaluate dramatically. Okay, so instead, if you look at the bottom down there, the second line from the bottom, before we had, with n equal to 5, we had 1008 plans. Now we only have 120 possible plans. Okay, now it's still a lot, by the way. Okay, if n is equal to 10, we still have this much plans, which is 3.6 million plans. Okay, so obviously, again, not all of these guys will be generated and evaluated. Okay, but at least we are restricting the search space a lot by just working with this variation of binary trees. Now, we come to the last topic really here, which is the system R. Now, system R, very popular in the database world. It's an implementation of everything we know that we describe today as a SQL database. It was done many years back by IBM, made IBM lots of money because of its popularity and how it was implemented. It had many innovative ideas. In fact, a lot of the ideas I have been describing in the course come from System R, at least in the last 3 lectures. Okay, now I'm telling you about it here. I'm describing to you here because many database engines are influenced by System R, including Postgres and including Oracle and SQL Server. And you would often see in the documentation mentions of it that this is a System R compliant part or module or whatever. Okay, inside the documentation. So, what did System R contribute? Why System R is so popular? Okay, why the optimizer for System R is so popular? First of all, it was the first one to introduce this notion of using left deep query plans. Okay, and as I've written there, instead of enumerating all possible plans and evaluating their cost, optimizer only looks for left deep query plans and you enumerate the different join orders. Okay, so this is coming from System R. Now, the second thing about System R is that it considers Cartesian products as late as possible to reduce I/O cost. This is a very simple idea, but turns out to be incredibly important. Cartesian products are the worst kind of SQL operator you could use. You should try to avoid it as much as you can because basically you are doing blind pairing of rows from two relations. So regardless of where you put your Cartesian product, it will try to throw it all the way up towards the root of the tree as much as it can, even if it's actually that means doing all kind of very weird and unexpected manipulations or inserting all kinds of other SQL operators to make sure that the Cartesian product is delayed as much as possible to avoid joining relations that have huge number of rows together. The third, and this is really the most complex part of System R, that I'm just going to give you a hint towards how it works, is doing something called bottom-up construction of plans. Okay, let me read the 2 points and then we will discuss it. It says 3.8 says optimizer starts by finding the best plan for one relation. It then expands the plan by adding one relation at a time as an inner relation. Okay, now for each level it keeps track of the cheapest plan per interesting output order as well as the cheapest plan overall. When computing the cost of a plan, System R considers both I/O cost and CPU cost. This sounds like very high level. What's the issue here? What I just described, for those of you who have been doing ACM problems will know that this sounds like dynamic programming, and it is indeed. It's the first actually optimizer that uses dynamic programming, which is an algorithm design strategy that you learn in CSAN 703. In other words, what it is actually doing, it is not really generating blindly trees or left deep trees and figuring out what's the cost of each and then picking the most optimal one. What it is actually doing, it is following a stepwise approach to build a left deep binary tree by picking from the different choices it has one pick and evaluating the impact of adding this pick to the left deep binary tree, and then continuing on with the second pick, and if it finds that the second pick is better than the first pick, it will replace it. So it is doing really dynamic programming in that sense. It's replacing previous choices by newer choices if newer choices are better performance-wise than older choices. And you can only do that really with dynamic programming. So obviously I don't have a space or an opportunity here to explain dynamic programming in detail, but that's really what makes System R a hit, and that's why people are still using it, because the tree construction mechanism is not blind. It's actually very aware about the impact of adding a new level in the tree to previous levels, and it only add a level if actually the performance is still the best it can get. Okay, so there is this notion of trying things out based on the impact on performance. Okay, it's not just building it and then evaluating it. While the tree is being built, performance is being evaluated, and if it suddenly figures out, oh, if I do this join now, instead of having 5,000 IOs, now I'm at 50,000 IOs. Okay, let's not do this join now. Let's actually do something else. So we pick another relation to do a join with, or do a projection, or do a selection based on the SQL. And if it says, okay, if I do this now, the 5,000 will become 6,000. Okay, let's keep it 6,000. Let's not go to the 50,000 now. Okay, so we'll try choices while it's building the left deep binary tree. Okay, now the fourth component of the R optimizer is that it considers what's called interesting order, and this is kind of you could think of it as a heuristic. We talked about heuristics before. It's like guidelines or rules to follow that if you do, more likely that you are on the right track. Okay, so let me read this. It says, if a query has an order by or group by clause, having results ordered by the columns that appear in those clauses can reduce the cost of the query plan because it can save extra IOs needed by sort or aggregation. Okay, so really the essence of this that will appear in later in many optimizer works, unfortunately we don't cover here, is this notion that if you know about the semantics of the SQL operator or the SQL function that you're invoking, you understand what they're really doing, then you can make better choices. Okay, so if you write a query that says order by, and that means you want the results to be ordered by this, and if this, what you're trying to order by, has a b+3 index built on it, then this means when you actually get the values, you will get them already ordered. So instead of running the query and then at the end running an ordering process or a sorting procedure, why don't you just pick the b+3 and work with it all the time? If the user already created an index on that column he's trying to order by, so that when you get actually the results, they're already ordered. Okay, and this is the essence of interesting orders. Okay, orders here does not mean necessarily sorting. It means the SQL operators. Okay, that if you understand the semantics, then you can pick a better, or you can pick not a better, but you can pick the you can bias your decision as a database engine towards picking a specific index like a b+3 or a KD tree or an R tree, because you understand the semantics of what the user wants from the SQL itself. Okay, so order by and group by were the two that were considered by system R, but we can think of many other variations. Okay, like count, for example, or minimum or maximum. Okay, so these things are all interesting because if you understand, or if you can associate, or if you understand kind of how the specific or the interesting things about a certain indexing data structure. Okay, for example, if the user groups by X and Y, 2 dimensions, and you support in the database engine KD tree, and the KD tree alternate the dimensions, so you could decide to have actually the KD tree because that will help you in the group by. Okay, so this is really what's called the interesting orders thing with system R.